All right, I've now started recording myself. Let's see. What are we going to discuss today? Great question. So I think today we're going to spend about 30 minutes or so and talk a little bit about the stuff that I had on the suggested exercises, and then we'll actually finally talk about quantum mechanics. So first we're going to start off with a tiny bit of review, like always, of things you've hopefully learned about in your analysis courses, right? Because you've learned so much in your analysis courses. I actually didn't check if the audio right now is like working properly. You know what? I'll actually stop. Okay, we continue. I'll stitch it together at the end. Okay, so what did you guys learn in your analysis courses? So let's first give a definition. Actually, let's maybe give a bunch of definitions. Let's see. True. Okay. Okay, so let's do some let's take a step back. Take a step back, maybe. And let's review what a metric is, right? So, definition. So, a metric space x comma d is a set x equipped with a function d, such that, and so the function has the following properties. So first of all, where is this function defined on? So if it's a metric, intuitively, what should this function tell us? Distance, okay. And if you tell me distance, what do I need to specify? What do the inputs have to be? 2 points, yes. We are going to be measuring distance between 2 points. Good. So distance. So it's gonna be from x cross x into where? R, but not just R, better. Yes. So essentially, yeah, R plus, and this I guess includes 0. So this is x and R such that x is greater than or equal to 0. Okay, straightforward. So I've kind of the positivity condition, before we'd when we defined the norm, I had like a positivity condition. Here, the positivity condition is like literally built into me defining the function to be from x cross x into r plus. Okay, what do I want? So okay, this is really built in. So positivity is kind of already in the definition. In definition above. Okay, what do I want next? Next, if I have the distance, well, actually, yeah. So let's go kind of in the order of the handout that I gave. So distance from a point to itself. What should the distance from a point to itself be? 0. Okay. Should the distance from a point to another point be 0 if they're distinct points? No. Okay, so the distance between x and y should be 0 if and only if x equals y. X and y are the same point. Okay, that's one thing we want. The other thing we want is if the distance between x and y is equal to something, then the distance between y and x should also be the same thing. Do you agree? That makes sense. And then you also want this is 3. And you want the usual thing, which is the triangle inequality. Okay, and so let's once again draw the triangle inequality. So, if I had a triangle with a line like this and a line like this, right? And this, right? So what do I want? Say this is A, this is B. No, this should be all labeled in white. A, B, C, right? So what do I want? I want the distance from A to B and B to C together. If I add those two, that should always be greater than what? A to C, right? So then I can write it like this. And usually people actually use X, Y, Z, so we'll do that. We'll do the distance from X to Z, so from A to C directly, should always be less than or equal to the distance from X to Y plus the distance Y to Z. Okay? So, this is kind of the red line, this is the green line, and this is the yellow line. Okay? Does this make sense? Yes? Good. All right. So now this is a metric space. Remember before we had the concept of a normed vector space, right? We had a vector space with a norm. And particularly what we were looking at an inner product space, and we used the inner product on the inner product space to give it a norm, right? So, okay. But a norm wasn't quite a metric, right? However, it turns out using a norm, I can define a metric. So let's see what this is. So I guess this is theorem. Some theorem that a norm on a vector space, is this visible? Yeah. Induces a metric via the following equation: dx comma y is equal to the norm of x minus y. Do you agree? Do people remember what the properties of a norm were? Positivity? Yes. Yes. And there was one more. That one more was the fact that I could factor out a scalar, and then I'd be factoring out the absolute value of the scalar. So in that case, from the definition of a norm, you kind of automatically get triangle inequality from the triangle inequality on this, right? Because if I added in some point in between, which is say z, I could do x minus z plus z minus y. So just do minus z plus z, and then use triangle inequality on those two terms, and then I'll get this. Good. Dxy dyx. Why does this work? Because remember, I can always factor out a absolute value of a scalar. So if I multiply it by minus 1 in the middle, I can factor out this minus 1. Yes? And if I factor out this minus 1, then it comes out as just a 1 and doesn't affect anything. In the norm. You may agree that x minus y is equal to minus y minus x. True? Okay. So this is really a minus 1, right? Times this. So now this has the property that lambda v is equal to absolute value of lambda times the norm of v. This is one of the properties in the norm. Minus 1 is a lambda. Absolute value of lambda is 1. Of absolute value of minus 1 is 1, right? So I can always swap the order of these and factor that out, and nothing changes. So I get dx minus y is equal to d of yx. Okay? Okay, and then this and this are like literally conditions in the definition of the norm already. Okay? So this is essentially, we proved this. It's just you have to remember what the properties of the norm were, the definition of the norm was. Okay, and now also yes. So really good point. A norm has to be on a vector space. Why? Because I just told you this whole thing of like the triangle inequality defined here is defined via what? It's defined as the v plus u is less than norm of v plus norm of u, right? So you have this whole idea of the fact that you can add vectors together, right? So the norm is defined on a vector space, right? The norm is something that's only on a vector space. A metric, however, can be defined on any set. A metric is a function on any set, right? But it turns out that if you have a vector space with a norm, that automatically gives you a metric, right? So a metric space doesn't need to be a vector space. But okay, norms are defined only on vector spaces, right? Because the whole point of a norm, it's this nice thing that works well with the addition and multiplication structure you have on the vector space. Like the norm is essentially something like a nicer metric, kind of, that works more nicely with the vector space structure. Of course, you can have different kinds of metrics you can put on a vector space, and that would still be fine. It's just that they wouldn't be as compatible. Okay, good. So this is something this is something maybe new, maybe old. Okay. Now, hello. Now, let's give a new definition. And this is a definition you've maybe seen in your courses already. Did you talk about like limits of sequences in 157? Okay. So in this case, you will be familiar with the concept of a Cauchy sequence. Yes? Okay. It's over. That's fine. So in that case, I'll even give you like an example, maybe. Okay, so let's see. The definition. And this is all in your exercises, these definitions, so that's okay. So let x, let xd be a metric space. Okay. A sequence of points of x. So it's x1, xn, and so on and so forth. It goes to potential infinity, and all of these points are in x, is called a Cauchy sequence if, guess what? For all epsilon greater than 0, there exists capital N such that for all little m greater than n, the distance between xn and xm is less than epsilon. Okay. So let's maybe think about what this means. Does anyone have a sense of what this means? That's actually a good point. Yeah. So yeah, exactly right. So the limit of dxn xm kind of, as you increase n and m, d of this quantity kind of keeps getting smaller and smaller. So in some sense, what this is saying, though maybe that's a bit harder to define this limit on these on two variables, but you're right in the sense that what I'm saying is, suppose I had these points. I have x1, x2, x3, x4. The point is that these points get closer to each other as you progress. So they kind of get closer and closer to each other, right? Or maybe you had something that was going like this, and then the points kept getting closer to each other, right? Okay. Now, following question. So yeah, does this definition kind of make sense, right? All of this is saying is that the points kind of get arbitrarily close to each other as you go along the sequence. Yeah. Okay. Now, following question. Does this? Oh, yeah, and also note that this is defined for like an arbitrary metric space, right? And actually, one thing that should be clear to you now, that you kind of have, I drew like a number line, right? So I drew an example on R, right? Where the sequences are points in R, right? What's the metric on R that you guys use? Exactly. So on R, the metric is x minus, just the absolute value of x minus y, right? This is also a norm on R, right? R is also a vector space, so that's fine. Do you agree? Yes. Yes. So a norm is defined on a vector space, and a norm, so on V, a norm it tells you the length of a single vector. So the norm, it goes from V to R. So it takes in a single vector and tells you how long it is. And it also plays nicely with kind of vector addition and vector multiplication, in the sense that, so you have like positivity, you have definiteness, and then the third thing is you have this property that I mentioned earlier. You have this property, the fact that you can pull out an absolute value of a scalar. Is this better? Okay. Also, the people on the video cannot see anything that I'm writing right now. Yes. So you can factor it out like this. And property 4 is the kind of nice compatibility with addition, that you get this kind of triangle inequality. A metric, on the other hand, it's something that doesn't necessarily, is not defined necessarily on a vector space, could be defined on any set. And it tells you the distance between 2 points, right? So here, this tells you the distance between of a single vector, and this tells the length of a single vector. This takes in 2 inputs and tells you the distance between 2 points. Why is that the case? Because on a vector space, right, look at how we defined it. I could look at the distance between 2 vectors by saying, well, the distance between 2 vectors is their difference, right? In a vector space, you can kind of quite literally think in terms of this diagram that I drew before, that the distance between kind of this vector and this vector is this vector, right? That's how you can. So I drew that diagram. The distance between this vector and this vector is this vector, and that's one way you can think of it. Actually, I should redraw this. I should draw it like this, and then I have a vector here, and I have a vector here, and then the difference should be this vector here. Do you agree? So in this case, if you draw this picture, then the distance between this vector and this vector is, of course, intuitively should be this vector, right? The difference between the 2 vectors. And so a norm, that's why a norm only needs kind of 1 input, right? Versus on a metric space is just some set. It doesn't have this addition and subtraction thing on it. So you need to really specify 2 different points to tell you the difference between it. versus a norm kind of exploits the fact that, hey, we have a vector space structure. It makes sense to add and subtract points, and uses that for help. No, you could be. I can look. Here's a set. 0. Here's a set. I don't know. Dot and star. That has 2 elements. Okay, I can clearly the distance between dot and dot is 0. The distance between star and star is 0. So I will define the distance between dot and star to be equal to 1. Okay, this is a metric space now. Right? You can any kind of points. You can just define a notion of distance by just telling me the distance between this point and this point is this much, and then hopefully the way you define your distances follows the triangle inequality and so on and so forth. But it's just a function. You can define a function on a set, surely. Okay. So Cauchy sequence. Cauchy sequence is that the points, as you go along the sequence, they kind of keep getting closer and closer to each other. Following question: does this mean that the sequence has a limit, in some sense? No. Why? Yes. Great answer. Depends on the metric space. Exactly. So sometimes it does have a limit. Other times it doesn't have a limit. And so let's look at an example. Also, we haven't even defined what a limit is in a metric space. But it's the usual thing. Why? Because just write down your delta epsilon definition for R, but instead of brackets, do D. Write D. So everything you've learned in like analysis about like I don't know, limits and all the definitions for limits and things like that, you can rewrite more generally for metric spaces just by instead of writing x minus y, just writing d of x comma y, right? And then it will probably be true for metric spaces, except for like some results that you showed about like compactness or something. Then you'd maybe need to use other language, but that's okay. Okay, so does what a metric make sense so far? Yes, it's just something that tells me this distances between 2 points. Yes, so we're going to look at that. Okay, so I'm not going to define what a limit is yet. I'll define it later just for completeness, but a limit is like, something that you get close to. Surely that makes sense. Okay, so I'm going to draw the following example. So example 1, let's look at R. Let's look at a Cauchy sequence on R. So this is 0. What's a really good sequence? Indexed by the natural numbers. Very, very good sequence. No, but that like doesn't get closer to each other. Instead of 1, 2, 3, you should do 1 over n. 1 over 2 to the n is too much. Just 1 over n. It's too complicated. I don't know what it means to like 2 to the n. That's so hard. So xn equals 1 over n. So let's draw this. Maybe I will shift 0 a little bit so I can draw easier. So 0. So let's do, okay, I'll have, say, 1 here. And I have 1/2 here. And I have like, I don't know, a third here. And I have like a quarter here. Okay, and it's going to get like closer and closer to 0, right? And you can, in fact, if you cared enough, what's the distance function here? The norm here is x comma y is equal to x minus y, right? Absolute value of that. That's our metric on this. In fact, induced by a norm. Great. Okay. So we get this. And so this converges. This has 1 over n has a limit, which is 0. Do you agree? And 0 is, in fact, a limit that is inside of R. Do you agree? 0 is in R. Okay. And this is a Cauchy sequence. Do you agree? However, now let's look at the following example. I'm going to take R, but what am I going to do to it? So I was asking you, do Cauchy sequences always have a limit? Right? Okay. So here the limit was 0. So now instead of looking at R, I'm going to look at R. Pardon? Sure, but just R without 0. So let's just take R and just remove 0 from it. I just took this point out. I had a piece of string, I just cut a piece out. Okay? But it's like exactly a singular piece of like a single point. Good. Guess what? I still have a metric on the space. This metric is still the same metric as before. It's still the exact same metric, well defined, has all the properties on here that you can check. And guess what? I still have the exact same sequence. Do you agree? So 0 is now omitted. And I still have the exact same sequence. It's like 1, 1/2, 1/3, 1/4, and okay, it gets closer and closer. But now, does this sequence have a limit? No, because 0 is not in the set. So it doesn't have a limit. But it's still a Cauchy sequence, right? So a Cauchy sequence is in some sense like the Cauchy sequence are like the sequences that should have a limit if our space is nice enough. And so now, finally, we get to the punchline of why I'm telling you all of this and why this is all so relevant to quantum mechanics. Because it is. Everything is relevant. Okay. Can I erase what a norm is? Do people remember what a norm is? I will erase what a norm is. Actually, wait. Let's talk about what a limit is, right? Because I told you like limits, so let's define a limit on a metric space. So let XD be a metric space. So definition. L is the limit of the sequence x1 to xn to whatever. If so, yeah. If what? If for all epsilon greater than 0, there exists an n in the natural numbers such that for all m greater than n, the distance from L to xm is less than epsilon. Right? So this essentially means that after a certain point, after a certain point, all of the points of the sequence are at least epsilon close to L, right? They kind of get trapped around L. Yes? Do you see how this is absolutely identical to the limits of a sequence that you learned in calculus, 137 or 157? Well, it's essentially identical, right? Do you see? The only thing that changed is if you were talking about R, you would write L minus xm. But I wrote DL xm, right? But actually, if anything, this is kind of more intuitive because L minus xm is like, oh, I'm taking some difference, I'm taking some absolute value, what does this mean? But here I'm telling you the distance between L and xm gets smaller. And telling me that the points are getting closer to L makes more sense than telling me that, oh, some numbers are small. I don't know. So this, okay? This makes sense, what this is? Yes? Yeah.
Is that going to come up?
Not necessarily. Well, you can have the space set X to be the set of complex numbers, right? You can still define a metric on it. It's just that the metric is always in R, right? Because complex distances don't make sense. We're trying to define something that's familiar, right? And I'm telling you that these four properties are like the minimum number of things that like you need to have something that resembles what we see in the world as distance. It's a really good shot of me, the camera. I look really good. Anyways, okay. Definition. Who would have guessed? Okay, I think we have two more definitions, and then we can start talking about quantum mechanics. So definition. A metric space is called complete if every Cauchy sequence has a limit. So remember, Cauchy sequences were the sequences where points keep getting closer to each other and kind of get the distance between them gets arbitrarily small. You would expect that this kind of thing should have a limit, right? If things keep getting closer to each other, then they should have a limit. The problem is that we looked at an example where you can just remove the limit from your space. The metric is still well defined. Nothing breaks. So sometimes that's not always the case. You might have points that keep getting closer to each other, but there's no limit in that space that they get closer to. And so now I'm telling you, you can have, let's call metric spaces complete. If it's a metric space where every sequence that we would expect to converge does in fact converge, right? So I'm telling you, we have this thing, these sequences should converge, but they sometimes don't. So let's look at metric spaces where that are nice, and this doesn't happen. So this is not a complete metric space. R, however, is a complete metric space. Okay? So it's kind of metric spaces where if some points keep getting closer to each other, then they converge to something. Yeah, there you have limits. Good. And from your analysis course, you should also remember that these limits have to be unique, right? You can't have on a metric space, you can't have a sequence of points, one sequence of points converge to two different points at once, right? That makes sense? Okay, why is that true? Which property of the metric tells you that you can't have a sequence converge to two different points? Yes. No. Well, maybe. Two. Yes. So essentially, how the proof would go is suppose you had two distinct limits, right, of some sequence, right, and they were both limits. But then you can kind of show that the distance between them has to be 0, meaning that they have to be the same point. So that's how you would maybe go about it. I don't know. But that's something that you will prove many, many times in like. It's a very simple proof, but for some reason, it's over. It's a very simple proof, but for some reason, you really start doing these things really more in 357. I guess you do have kind of examples like this in 157, but you don't think about it as much because R is just so nice. Anyways, this makes sense. Okay, now finally for our last definition. A Hilbert space is a complete inner product space. So where the metric is defined in terms of the norm. So recall, so dvu okay. So remember that we had these, we had a vector space, and then we said let's put an inner product on the vector space. Remember that? We had inner products on vector spaces. And then we said, okay, well, if I have an inner product, that actually defines a norm on that vector space. But we just said that I may have erased it. We just said that a norm on a vector space also defines the metric. So if you have an inner product space, then not only do you know what lengths of vectors are, you also know how, so yeah, you not only do you know how long vectors are, you also know what the distance between vectors are. So an inner product kind of tells you everything, right? And this is kind of a good hierarchy to think of it on, is like an inner product gives you a norm and a metric. A norm always gives you a metric, and a metric does, yeah, but a norm doesn't necessarily give you an inner product. And a norm and a metric doesn't always give you a norm. So, yes. Because maybe I could define my distances in some nonlinear way, which would be weird. Like, R2 is a vector space, right? But then I could think of R2 as like you put it on top of a sphere, and then you can have distances like that way. Just think of, you have like a sphere, or like a surface, like a sheet of paper, and then you have a ball below it, and then you just like push it up, and then have the paper wrap around the ball, right? And then you can define distances using the distances on the ball on your vector space. But then that's clearly non-linear. That's clearly not a that clearly wouldn't give you a norm. Or just don't think about what I said. Okay. Yes. No, it's really not that bad. I just don't have a ball of some sort. Like, does anyone have like a piece of paper, like a loose piece of paper? Yeah, sure. Give me your notes. Okay. So suppose this is like perfectly spherical, right? Then suppose I wanted to look at the distance. So let me look at it. So suppose I wanted to look at the distance between, say, this point and like this point on my sphere, right? How would I do that distance? I'd look at the shortest path going like along the sphere from here to here, right? So I could define a distance this way on the sphere, right? But then if I had a plane, right, what can I do? I can take this plane and kind of wrap it around the sphere, and then say, okay, this point on the vector space would get mapped to, say, this point on the sphere, and then this point on the vector space would be mapped to, say, this point on the sphere, right? And then I can use the notion of distance on the sphere to define a notion of distance on the plane, on the piece of paper, right? But clearly, since this is like curved, right, and this is flat, clearly this is not going to work nicely with like the scaling of a norm, right? A norm you can always scale by lambda, and then that scales the length of a vector. But if it's like this, then that whole scaling thing doesn't work. Because like, what does it mean to scale something on a sphere? It doesn't make sense. Yes. Yes. Well, except for I'll have to miss one point on my fist. Yes. I'll be stretching my fist to like fit most of the plane. Yes, you're formerly a flat piece of paper. Okay. But now, do we understand what a Hilbert space is now, right? So we had this inner product. An inner product, remember, it told us something about angles between vectors, right? Because I have yellow chalk on my hands. Crazy. Yes. So remember, an inner product space, it was a vector space with an inner product, and so that told us something about like angles between different vectors, right? we also notice that it gives you a norm. It gives you a notion of the length of vectors. Right? Today we notice that this gives you a metric, which tells you the distance between two vectors. Right? So an inner product space is this thing that where you know like angles, you know lengths, and you know distances between points. Good. And a Hilbert space, it's an inner product space which is complete, meaning that if you have a bunch of vectors that keep getting closer to each other, then they have to have a limit. Okay? So that's all a Hilbert space is. Now, sometimes, and especially in older literature, a Hilbert space would be defined as a separable complete inner product space. So in some sense, it meant that it had to have like a countable basis. But we will not necessarily investigate that because in quantum mechanics, you often have non-separable Hilbert spaces. And so we need to account for that as well. But those are words that mean nothing to you, so don't think about it. Only think about this. Yeah, so complete is the bit. No, so I'm saying if I had any Cauchy sequence, right? So if you give me a sequence and it happens to be Cauchy, then it has to have a limit. Right? Because you can think of like, oh, what are all the possible sequences on my vector space, right? Some of them, well, yes. Yes, a sequence of points is what I mean, right? So this is saying a metric space is complete if every Cauchy sequence has a limit. So if you can write down some sequence and it turns out to be a Cauchy sequence, meaning the points keep getting closer to each other, then there has to be a limit. It has to converge to something. Okay, then you're good. Perfect. Let's look at an example of a, but you always have Cauchy sequences. You always have the trivial, yeah, where you just have x, 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 x forever. Apart from those, well, true. For example, you have the space with dot and star, right? Dot and star, the only Cauchy sequences are dot 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 or star 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 star, or where initially it's like a few dots and then only stars, right? So you still have a lot of different Cauchy sequences, but all of them eventually just become dots or just stars, right? Yes, but you know, so this is then in fact a complete metric space, right? The space of dot and star, where the distance between dot and star is 1, is complete because all the Cauchy sequences you have are just star 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 and dot 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 dot, and those converge to dot and star, respectively. Okay. Pardon? Ooh. It's probably true, but I don't want to think about it. Well, yes, because yes, of course, because you can't have points getting arbitrarily close to each other, because you always have a kind of minimum distance, because you can just look at all possible pairs of points, and there's finitely many, and that means you know that whatever sequence you have, if it always has different points, then there's like a lower bound. So the only way for things to keep getting closer if it's the same point with just zero distance. Okay. Good. Yes. So is this okay? We have a sense of what Cauchy sequences are and why we care about complete metric spaces, right? Okay, I will erase this now. And now we can talk about quantum mechanics. So there are many ways to introduce quantum mechanics, right? There's many interpretations of quantum mechanics. There's in fact a course on interpretations of quantum mechanics in the physics department, Physics 491, which I recommend everyone take whenever they are able to. And kind of in that course, one of the first interpretations of quantum mechanics that you talk about is called, is my microphone still on? is called textbook quantum mechanics. Why? Because this is the way that they usually introduce quantum mechanics in textbooks. And so that's what we're going to do. We're going to kind of follow this usual way. And then we'll maybe make some comments about, there's definitely issues with quantum mechanics on like a philosophical level, for sure, and many other levels. But maybe I will not make the best comments about it. But for now, let's just try and understand textbook quantum mechanics at first, and then we can actually think about it. So the way that people usually talk about introduce textbook quantum mechanics is by a set of postulates, right? So in a kind of very, you can think of it in a very mathematical way, where you just kind of have you have your axioms, you set up your thing, and then you work with that. So let's look at the postulates of quantum mechanics. This is the reading that I asked you guys to try out in Cohen Tanuji. Cohen Tanuji, no one likes that book, at least like as far as learning quantum mechanics goes. And I can't really comment about it because the only thing I've read in that book are the 6 or whatever postulates. I read those 10 pages and I've never read that book again. I've in general also not read that many quantum mechanics textbooks. As you can see, I've been mostly reading linear algebra and analysis textbooks instead. Okay. So, does anyone vaguely remember, out of the people who did the reading or tried to do the reading, what the first postulate is? Pardon? In state space, maybe. Yes, cat. Okay. Yes. Yeah, that's fine. That's how it's supposed to be. But also, these symbols were supposed to be familiar to you, because you've seen something that looks exactly similar to them in what we've been talking about. Okay. Okay. So let's see if there's okay. So for now, I will omit this. Maybe sure. So let's do postulates of quantum mechanics. We're not going to talk about all of them today. I want to go slow. So let's look at postulate 1. So for now, we're going to kind of restrict our attention to stuff that is happening at fixed time. So the state of an isolated the state of an isolated system is described by a vector also often called a ket in some Hilbert space. In some Hilbert space, let's call it H. Agree? This is postulate 1. And so, yes. And so, sometimes people usually denote this as some psi of T naught like this. So we write our vectors like this, right? Instead, I could have written V, right? I could have written U. I could have just written psi, but you add, this kind of line and this kind of bracket, right? We will see in a moment. Well, actually, yes. The reason is fairly simple. So remember how we had an inner product between two vectors, u and v, right? and I'd write it like this. Okay, but now, because for a physicist saying, oh, an inner product is some function that's defined on v cross v and has these, that's too complicated for a physicist. So what physicists say is that for every state there's a ket and then there's a bra. And if you write the bra and the ket next to each other like this, then this gives you the inner product between psi and psi, or and phi, or whatever it is. So a ket and bra, they're written like this, so that this is equal to like the inner product between phi and psi. And it's just, you don't have to kind of differentiate the fact that there's a whole inner product thing. It's like a notation, so that this means that. And so you kind of like write this automatically with like this added bracket of the inner product, because for fun, I guess. Well, not for fun, there's some reason, but this is one cheap way of understanding it. Right. Also, the other thing is, so remember how in our Hilbert space, so when we defined inner product spaces, we had the following property. So we had u and, no, sorry, we had u plus lambda vw. So it was linear in the first entry, right? Right, we had that the inner product was linear in the first entry, and then you had this conjugation property that if you wanted to swap two entries, you had to also get a conjugate. Remember that? So in physics, they do the same thing, but in physics, the inner product is defined to be linear in the second entry instead of the first entry. So it's the same thing, but if before you could pull out a scalar from the front, from the first entry, and then you'd have to pull out a complex conjugate of the scalar from the second entry, now you do the opposite. But okay, so that's confusing. I will use the two interchangeably, I think, and so that should make sense. But yes, so do people see the difference between being linear in the first entry versus being linear in the second entry? Right, because before, if I'm linear in the first entry, then lambda uv is just lambda uv, right? And if I did u lambda v, this would be lambda bar uv, where this is the complex conjugate of lambda. Right, so this came kind of from this fact. Right? But now if I am linear in the second entry, then this would be reversed. Right? So you'd have the skew symmetry will be in a different entry. Okay, but that's really the same thing. I'm just kind of saying, oh, instead of writing stuff on the left and right, I'll write stuff on the like right and left. It's like, am I plugging in the vector into the left and then here, or am I just swapping which way I plug stuff into it? It's really the same thing. It has all the same properties, up to rewriting something. Okay. And we often denote these vectors by some letter, and then you write these funny brackets around it. Okay. This is postulate number 1. So what does this postulate tell us? Thoughts, comments, like, tell me what this is. Tell me what this means.
I think it's just a full description.
Exactly. Exactly. You came to my office hour last year. Yay. So the state of an isolated system is described by a vector in some Hilbert space. So what this is saying is that, suppose you had some kind of system, and there's something to know about it. Well, guess what? If a system is in some state, then all of that can be represented by some vector in some Hilbert space. Okay? This is what this postulate is saying. A state is like, it's the state of a system, right? The state of being. Like, a ball can be red or blue, right? It can be in the state of being red, or the state of being blue, or the state of, other things. And we're saying that all of this can somehow be fully encapsulated in a single vector of some Hilbert space. Some Hilbert space. So some vector space where you have an inner product and it's complete. Yes? So let's maybe think about why the Hilbert space, why the vector space has to be complete, right? Why is that? Well, maybe let's look at a ball, a red ball. Suppose that my ball could be red, but it also could be slightly darker red, and then slightly darker red, and then you change like the hue of the redness such that it converges to some very particular red, right? So then surely my ball should also be able to be like that particular kind of red as well, and that should also be allowed, right? So that's why you want the vectors, if they are converging to something, if they keep getting closer to each other, that that should also be allowed, right? Not necessarily. Well, like yes, there should be a state which allows that to happen. Yes. But then you could also make an argument with position of like if my ball can be here, it can be here, and it can be here, 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 and it keeps getting closer. It should also be able to be like somewhere close to there, like to wherever it converges to. Maybe something like that. That's like some intuitive motivation, which might also be wrong if I think about it enough. But okay, my point being, do you believe that a Hilbert space, like why we want these vectors to be in a Hilbert space rather than just an inner product space? No? Why do you not believe it? Yes. Mm-hmm. Yeah. No, I'm not saying that he's actually going to reach the finish line. Is that it is possible for him to be at a finish line. Like there exists a state where like if the guy is allowed, like there is a possibility of the guy standing here, and there's a possibility of the guy standing here, and there's also some configuration in which the guy is here and here and closer, then there should also be some possibility, some state, such that the guy actually gets there. It doesn't mean that he will actually get there. It's just saying that it is an option. Him being there is an option. It's like something that could, in principle, happen. I don't know if that's satisfactory. Yes. So, okay. If you have a system, what it can be is sort of like its state is somehow described by a vector in a Hilbert space. Okay. So this is postulate number 1. Now, so maybe this will clear up some difficulties. Or maybe it will introduce more. It should probably introduce more. So right now, I told you that this vector kind of tells me everything. It somehow encodes everything possible, right? About what the state can be, right? But at the end of the day, this is not that helpful, right? This postulate on its own is kind of useless. Because at the end of the day, what do I want to do? There's only one thing I want to do at the end of the day. Which is? Sure, exactly. Well, I want to do an experiment and measure something and be able to predict it, right? At the end of the day, I want to do an experiment. And this does not tell me at all how I can predict anything for an experiment, right? So now the next few postulates will kind of be there to try and help me, do an experiment and predict something in an experiment. So this very abstract Hilbert space of like these states that the system could be in, whatever that means, we need to relate that to reality somehow, right? So we need compatibility postulates between quantum mechanics and my sensations of like the classical world. Okay? And maybe later I'll reorder the postulates once we get through them, maybe next time. I'll reorder them and kind of point out that you can in some sense, think of some of these postulates as like, here's the quantum mechanical ideal world, and then here's the postulates that kind of connect it to like experiment and the real world, like compatibility postulates. Remember how for a vector space I was also kind of talking about compatibility, where in a vector space you have some axioms of addition, some axioms of like scalar multiplication, and then we have some compatibility axioms to make them work together. So this is not at all like that. But well, look at this postulate. This postulate is saying that the state of a system is described by some vector in some arbitrary Hilbert space. How do you do an experiment to see some Hilbert space, right? This is some realist picture. Like, this is me saying that, you know, there is some world out there that our theory is trying to describe, which looks and works in this way, but it's not like, you know, I can take this Hilbert space and look at it. Can't do that. That's why it's a postulate. You just assume this to be true without. You're not supposed to explain it. I'm trying to explain things that maybe shouldn't be explained. Okay, 2. So let's think about how to phrase 2. Any physical measurement, or well, yeah, I'll do it like this. I'll do it. Yeah, any physical measurement has an associated self-adjoint operator let's call it A. So it's an operator from the Hilbert space to the Hilbert space. Well, I guess a joint linear operator. Let's say linear operator. Where so called the observable. So called an observable. Okay, so this is not kind of the full story quite yet. We'll get to this in a moment. But this is the second postulate. Okay. So postulate number 2 and then like the next couple postulates really should be combined into like one big thing, but that's okay. So now I'm beginning to try and relate the real world, this quantum mechanics Hilbert space world to our world. And I'm telling you the following. If I can do a measurement in real life, so, you know, I can have some gadget and, you know, it has some dial, and then I can, you know, press a button and the dial, you know, makes a measurement and moves to, you know, some position. I can read off what it says on that dial. I'm telling you that if there's something like that that I can do, then in the quantum mechanical world, there has to be a self-adjoint linear operator associated with that. Okay? So if I can do a measurement, so such as measure the energy or measure the position of something, then that has to have a self-adjoint linear operator associated with it in this quantum mechanical world. Yes?
First time I'll read the thing. What does self-adjointness have to do with any of this?
Self-adjointness? Well, we'll see in a moment. But remember, so this is potentially infinite dimensional, but remember, what was so nice about self-adjoint linear operators in finitely many dimensions? What was the big theorem that we proved? The spectral theorem. So we showed that any self-adjoint linear operator has a basis of eigenvectors, right? So now, good catch. So a good catch that this has to be self-adjoint, right? Before we proved the spectral theorem, and the spectral theorem told me that self-adjoint linear operator in a finite dimensional vector space has a basis of eigenvectors, right? So now the postulate number 3 is going to tell us, you know, how to use this observable to actually compute something, and it turns out it relates to the eigenvectors and the eigenvalues of the observable. Right. So now whenever I say observable, I mean some self-adjoint linear operator that is associated to a physical measurement you can make. So you can think of it. So you can think of like, you have quantum mechanics, like quantum mechanical world, and so me, right? And so in the quantum mechanical world, I have a Hilbert space. Here, okay, that doesn't really relate to anything here. And then in here, I can do a measurement with a gadget, right? It has like a dial, has a dial. So measurement. Okay, and this is observable. The thing that is associated with that is an observable, which is a self-adjoint linear operator from H to H. Self-adjoint means that, well, the adjoint is itself. So A dagger is equal to A. Okay. Yes. Do you not remember what self-adjoint was? Okay.
What is the, are you saying the spectral theorem is what important for this postulate?
So we'll see. So we're going to write down the next.
Like why it is.
So well, because I didn't tell you the punchline yet, right? But do you understand that the postulate tells me that if I have a physical measurement, then there must be an associated self-adjoint operator to it. Okay.
Bunch of numbers that you collect
No, no, no. I'm telling you that suppose there's a physical process that I can do. Say, take a meter stick and look at, the distance between, like a physical measurement. No, no. I'm like, suppose there's a physical measurement I can make. So some process, and at the end I get a measurement, like a number, right? So this process of measuring something in the real world, there's something that's associated to it. By associated, I mean it's just that there's related. Like they're related in the sense that I can just match them, not in a sense that they're like in any mathematical relation. Meaning that, okay, if I have some process of measuring something and I can measure something, then there must be a self-adjoint linear operator, and I can say that it's associated to this measurement. And how it's associated to this measurement, I'll say in a moment. Yes, but you never really map. You never. Well, that's the thing. It doesn't. It doesn't. It doesn't transform it to the other state, because you always want your states to be normalized, and observables are not generally unitary. So you never really want to look at a state after you've applied an observable to it. You maybe want to look at the inner product between A applied to some psi with something else, but you never really consider the state with an observable applied to it on its own. You never really think about that. Yeah, but that's not sure. But that's not the same. That's not the point of the postulate. But I get that is important, but unrelated. Okay, so now I'll continue this postulate. So how does this observable at all relate to real-world measurement, which is, I think, what you've been asking? Okay. And it tells us the following. So A, so the eigenvalues of A are the possible outcomes. So give the possible outcomes. Give the possible outcomes of the measurement. So this is the first part. So I'm telling you that, okay, if I can do a measurement in real life, then in the quantum mechanical world, there has to be some self-adjoint linear operator, and the eigenvalue that is associated to this measurement, and the eigenvalues of this operator will tell me what can I measure in the real world. Okay? That's already pretty good. Okay? This is step one. Yes? No, it does not. And an observable is just something that encodes what you could measure, but it doesn't represent actually doing the measurement. When you actually do the measurement, something else happens, and that's a separate postulate. Okay? Okay. But I don't know if we'll try and get to it. Is this board movable? Yes. I will erase this. By now, everyone should know what a metric is, what a Hilbert space is. You had a whole 40 minutes to digest. So, right? This is exactly what university is about, right? You have to understand everything in the shortest amount of time in like 5 minutes. If you don't understand something in 5 minutes, then it's over. Of course, that is a lie. Anyways. Good. So this is part one. The next part of the postulate, part two. Well, actually, this is in Cohen-Tanuji. This is like a whole separate postulate, but I'm gonna like bulk them all into one big thing. So part two is, so suppose your system is in some state, say, I don't know, state V in the Hilbert space. So I'm not using the fancy bracket stuff for now because I don't want to. Okay, so suppose this is the case. Okay. So let A be an observable associated to some measurement. To some physical measurement. Okay? Okay. Then the probability to actually, you know what? Let's do this. Let's do psi. So let's call our state psi to be more conventional. Okay, I'm just not writing the like bra and cat fit. Okay, so then so suppose our system in a state psi. Suppose we know what this is, and A is an observable associated to some measurement. And then the probability to measure lambda in the state is given via the following expression. So the probability of getting lambda is going to be the sum over the absolute value of the inner product of, okay, now I need to use the math convention, right? So I'll use the physics convention so we don't get confused. Or maybe we will be confused. Actually, it doesn't matter what convention you use. Vi psi all squared. Sorry, is that the case? Yes. Vi, where Vi are all eigenvectors of A with eigenvalue lambda. Whew, okay, this is a lot. I'll give you a moment to read this. Oh, well, sure. I can just do V. Up to you, but VI I feel like is better. I don't know. Because when I write I, that kind of implies that this is like countable, but it might not be countable, but it's like it is countable, but it's also not always a sum. I'm being a little unclear here for a reason. For now, this is all supposed to resemble like a finite dimensional vector space. I'm writing everything as if H was like finite dimensional or like had countable dimensions, but okay, because that's what we're most familiar with. Okay, so finish copying and then we'll discuss. Yeah. Oh, I forgot to mention an important thing. In state psi, and the norm of psi is equal to 1. And so we will always look at normalized states, and we'll see why later. But actually, it makes sense why you want to be in a normalized state. You want to be in a normalized state because, see, probabilities are somehow related to inner products, right? So if you're in a state psi and you want to, suppose you make a measurement to check if you're in state psi, then if you're already in state psi, then the probability of that should always be 1. So the inner product of psi with itself should be 1, because if you have some measurement, well, yes, okay. Suppose you had a physical measurement which checked if you're in state psi, and so if you are in state psi, it output 1 and 0 otherwise. Do you agree? So then the observable associated to that is going to be something that takes psi to itself and any scalar multiple of psi to itself, and then everything else to 0. So it like projects onto the subspace. But then if you have this projection observable, right? You want, following this postulate, to have, and all the VIs are also normalized. Are eigenvector are normalized, so unit eigenvectors, I guess. So are unit eigenvectors. So when I say that, I mean that the norm of V is 1. Sorry, these are bits that I always forget, but they're important. So, well, remember, this is a self-adjoint operator, and you can show from the exercises that if you have a self-adjoint operator and then you have eigenvectors, distinct eigenvectors, then they have to be pardon? Not in this sum.
I don't know how to say what.
So you can have, in principle, you can have an observable that has the same eigenvalue and has different eigenvectors with the same eigenvalue, right? You know, I can always write down a matrix which is like 2, 2, 2, and then 0 everywhere else, right? This is Hermitian, this is self-adjoint, this is whatever, this has 2, 2, 2. But it has different eigenvectors, but all with the same eigenvalue. And so what I'm saying here, okay, let's start again. Suppose I know that I am in some state psi, right? So suppose I know I'm in some state psi. Now, suppose I have some measurement that I want to do on my system. And suppose, okay, so measurement. So from the second postulate, I know that to this measurement that I can do in the real world, there is an observable in the quantum mechanical world. Do you agree? Okay. From part A of this postulate number 2, we know that the eigenvalues of this observable will tell me the things I can actually measure. So the eigenvalues of this observable will tell me the readouts that I could possibly see on my device. Do you agree? Okay. So now I want to see, okay, if I'm in state psi, what is the probability that I measure some lambda? So that I measure to be in like a particular eigenvalue of my observable, right? The eigenvalues of the observable are the things that I can measure. So let's pick one eigenvalue. So let's pick one thing I can measure, and let's look at the probability that I measure that thing, right? Okay. Well, it turns out that this probability of measuring lambda, right, in the real world is given by this expression where I'm taking the squares of the inner product of an eigenvector that has lambda as an eigenvalue with the state I'm currently in. So I look at all the eigenvectors that my observable has, that has the eigenvalue that I want to measure, inner product it with psi, square it, and sum over all the possible such eigenvectors with that particular eigenvalue. Right. So recall. So I specifically said that the VI are normalized eigenvectors. So I scale VI's to 1. So I scale VI's to sorry. I scale VI's to 1. I scale psi to 1. Right. True. How do I? Right. Why? Because psi is because psi has norm 1. VI are eigenvectors of a self-adjoint operator, so they have to be orthonormal to each other, right? Do you agree? So in some sense, I should be able to write psi as a linear combination of these guys and maybe some other guys. Do you agree? So overall, it has to be less than 1. So the important bit is that this. So this is a good question. How do you know this has to be less than y? 1. It all depends on the fact that the VI's are all orthogonal to each other, and that's something you proved in the exercise. That if you have a self-adjoint operator, then its eigenvectors are always orthogonal to each other. Yeah. So then you should be able to express psi in terms of these vectors and some other vectors that you add to complete the basis, right? And then you get, since psi has norm 1, this has to be less than, has to have norm less than 1, okay? So this is already getting somewhere. Okay, so now what this tells you, what does this tell you? This is saying, suppose I had a measurement that I could make in the real world, then it has an associated observable. Using that observable, if I know the eigenvalues of the observable, I can figure out what are the things that I can measure in real life. And then if I know what state I'm in, I can even look at the probabilities with which I can measure something. Okay, so this is pretty good. However, we still have not actually made any measurements. Right? So far, I told you that if I had some procedure to do a measurement, then here's how I can tell you what I could possibly measure, and here's what probability that I could, that I would be measuring something with. But we didn't actually talk about, the physical process of actually making a measurement, right? All of this is still kind of in this kind of, quantum world of Hilbert spaces, right? All of this stuff, like this observable, these eigenvalues, all of this is in whatever. This so far doesn't directly interact with the real world yet. And that's where we will need the fourth postulate. So the fourth postulate oh, sorry, not the third postulate. Sure. Postulate number 3. Okay. Suppose I have a setup as above. So setup as above. So my state, I'm in state psi in the Hilbert space, with the norm of psi being equal to 1, right? So measurement associated to observable A, right? Okay, we have some eigenvalues, whatever. Now, suppose I actually do the measurement in real life, and I measure lambda. So now, suppose I do measurement, and measure lambda. Then my state changes into the following. So psi gets sent to the sum over these VIs okay, okay, now this actually starts to matter. Okay, so where okay, so write that down, read it, and then we'll think about it, and then we'll stop. Yeah. Absolute value of what? This? The inner product? No. The inner product could be complex. The inner product is only positive if it's a vector with itself. But these are two different vectors. So this could in principle be a complex number. Not only could it could be negative, it could also be a complex number. But you really want your probability to be positive. Yes. Until you read like the Twitter posts of people talking about negative probabilities in quantum mechanics, because like Feynman made some remark that used those words in a similar order, which meant something else. I never actually read the article, but that was something people were discussing on Twitter a while ago. He went academia Twitter. Okay. So now this is what you were saying. So remember you were asking about, do you apply A, like what happens once I do a measurement? So the observable A, it just tells me the possible things that I could get out of a measurement, and it tells me how I would, so that's what its eigenvalues are. And I then use the eigenvectors to compute the probability of measuring a certain thing if I know what state I'm in, right? But now if I actually do this measurement in the real world, then what happens is the state changes from psi into projecting psi onto the subspace that has eigenvalue lambda. So why does this make sense? I will draw. We will do. Right, and we also wanted. Sorry, we also wanted all these VI's to also have norm 1. Okay. So why? What is this? Also, do people understand when I write these two dots, these two things? So the norm with a dot inside, I mean that just put whatever is at the top of the fraction into here. So I'm normalizing it. I'm dividing it to have norm 1. Right? I do something to it, and then I divide to have norm 1. So what does this mean? Remember, just recall that if I have an orthonormal basis, like some orthonormal, if I have an orthonormal basis W1, say up to Wn, right? So if this is orthonormal, right? If this was orthonormal, then any V is equal to the sum of W1 with is equal to the sum of V with W1, Wi. Oops. I. Do you agree? Right. Remember that if I had an orthonormal basis, then the inner product would tell me the coefficient in front of the basis vector in the expansion. Yes? This is something we proved a while ago. So what this is saying is, okay, if I measure lambda, right? If I measure lambda, then there are particular eigenvectors that have lambda as its eigenvalue. Right? There are particular eigenvectors that are associated with lambda. So what I'm going to do, I'm going to take my state, look at the bit of my state that had lambda as the eigenvalue, and just leave it at that and normalize it. So Vi, because because the Vi's are eigenvectors of a self-adjoint operator, Vi's have to be orthonormal, right? And so these Vi's, they specifically have eigenvalue lambda. So I can take these Vi's and then extend it to some orthonormal basis, right? And so what this is saying is I have my vector, I can write it in terms, I have my vector, I can write it as, I can expand it in terms of a basis where the first bit is Vi's, and then the rest is some other vectors, right? And so this first set of Vi's, these are the eigenvectors with eigenvalue lambda. And so what I'm saying is, if I actually did measure my state to be an eigenvalue, to have eigenvalue lambda in my measurement, then what I'm doing out of the expansion of my vector, I just kind of drop this bit entirely that is not related to lambda, and just keep the bit that is made up of eigenvectors with eigenvalue lambda, and then normalize it to have length 1. Yes. So not all of my eigenvectors have to have eigenvalue lambda. Some of them could have a different eigenvalue, right? So I can then just add more vectors to extend it to a basis of the whole space, to an orthonormal basis of the whole space. And then I can take my vector and rewrite it in terms of that. So let me do this properly. So let me explain this properly. So suppose we have, AVI is equal to lambda VI, right? So this is what it means for VI to be an eigenvector of A with eigenvalue lambda, right? So because A is self-adjoint, V1 up to, some Vn, maybe there's more, maybe there's infinitely many of these, doesn't matter. These are orthonormal. Okay? So now I can extend two bases. Two bases. So, okay, and this, whatever. So the first n of my vectors in my basis are these eigenvectors of A, and the rest are, some other vectors that I add to it, right? What does this mean? And so this is still orthonormal. Okay, now you can't actually always do this. You can't always choose an orthonormal basis of eigenvectors because you can have like a weird Hilbert space. But I'm kind of thinking about, nice stuff that's almost finite dimensional or close to it. Well, think about it like it's finite dimensional. Okay. So now I know that then my state psi can be written as what? As psi inner product v1, v1 plus. Yes.
When you're extending to a basis, does that just mean the other W's are together all that one
For the whole Hilbert space, yes.
for the W's?
Or a Schauder basis, maybe not a basis, but just a base. It's like a basis. It's like a basis.
Is it, are the W's orthonormal?
Yeah. So I'm saying that suppose that these were orthonormal and had eigenvalue lambda, then we can take this and extend it to an orthonormal basis where all of these are orthonormal with respect to each other. So, suppose we're in a Hilbert space where you can necessarily do that, because that's nice examples. Okay, then I can write out my vector like this. It's the vector inner product v1 times v1 plus vector whatever plus vector inner product vn times vn, and then plus the same thing with the w's, right? Okay. What I'm saying is measuring lambda just keeps this bit, forgets this bit, and then divides to make it have length 1. So if I measured lambda, then my state psi becomes this new state, which is v1 plus divided by the norm. Do you agree? Yes. No. No, because these v's are the eigenvectors of A that have eigenvalue lambda. There could be more eigenvectors. Right? Yes. Orthonormal. So yeah. Okay. Okay, so we'll now try and wrap up and summarize everything we've done. So what's one thing actually that I didn't mention yet? So I told you stuff about measurement. What's one assumption that we made at the very, very beginning? So isolated is a really good point. I will talk about that later. What did you say? Complete a bit later. What assumption we made about psi? Psi describes the state of an isolated system at some time, at some fixed time. So far, everything I told you happened at some fixed time t0. I have so far not told you how a system evolves in time. Do you agree? But okay, we'll talk about that later, because that's too much. So far, I've only told you about something that all happens in an instant, right? Where I'm assuming I can do a measurement in like an instant, but not whatnot. Okay. So let's summarize. We have states. So let's go back here. We have states. And if we are in an isolated system, then the state of the system can be described by some vector in some Hilbert space. That's postulate 1. That whatever we're doing, we're working over some Hilbert space. Good. Then I'm saying, suppose there was something I can measure in the real world. That means that associated to this measurement in the real world, there has to be some self-adjoint linear operator associated to it, and I'm going to call that an observable. Okay. So why did it matter for it to be a self-adjoint linear operator? Because a self-adjoint linear operator over a nice enough Hilbert space has a basis of eigenvectors and of eigenvectors, right? And that's what we're kind of using later. Anyway, so okay, the eigenvalues of this observable will tell me the things that I can actually measure in an experiment associated to this that does this measurement. Right? So if I do this measurement that the observable is associated to, then I can, on my dial, I can read the numbers that are the eigenvalues of the observable. That makes sense so far, yes? Okay. Then I say the following. Suppose that my system was in state psi, and this is a normalized state, so the state has, it's a vector with length 1. Then, and I had an observable associated with some measurement, then the probability to measure lambda in the real world is given by, this formula, where I take inner products between my state and the normalized eigenvector of A that has eigenvalue lambda. Let's also very briefly look at this. So Vi inner product psi, right? What is this? This is the coefficient in front of the expansion of psi in terms of this basis, right? So in fact, if my state psi was some superposition of if my state psi was some linear combination of v1 up to vn, right? Then the probability to measure eigenvalue lambda is just the sum of the squares of the coefficients in front of these guys. But this is if the VIs are orthonormal eigenvectors with eigenvalue lambda of A. Okay? And then I said, okay, now suppose I actually do them. So this is just telling me the probability if I did this measurement, right? If I was to do the measurement, what's the probability that I actually measure this eigenvalue lambda? But if I actually did this measurement, what would happen to the state? It turns out that if I actually do the measurement, then the state collapses to only the part of itself that was made up of eigenvectors with eigenvalue lambda. If I measure lambda in the real world, then the state collapses into something that could only ever give me lambda, right? And this is kind of what this is saying. Like initially, my state, in my state, I could have a probability to measure multiple different things. But once I measure my state to have lambda, then the state collapses and turns into something that only gives you probabilities to measure lambda and nothing else. Okay. So this is an overview of some of the postulates. We will do an example next time. And I think I will write up this example in your suggested exercises today, or maybe soon. And then we will just do this exercise together in the future, in a bit. Or maybe I'll do 2 exercises. Yes? Good. Remember, we wanted our states to be normalized. Why did we want them to be normalized? So that when we compute probabilities using this formula, we got probability of 1. So you always, a state, like I say it's a Hilbert space, but actually you aren't quite working with a Hilbert space because you're kind of working with like a projective space because you're only considering states with norm 1, right? What are states with norm 1? That's like a sphere in your vector space, right? So really the vectors, the states you could be in really always have to be norm 1 because you always want to have probability of, if you're in a state, then you should have probability of 1 to be in that state. You know what I mean? Like it's a kind of tautological statement. But That's what you would want. And so so to have probabilities add up to 1, you need all of the states that you work with to be normalized and have and have norm 1. Now the reason why we wanted to have the observables be self-adjoint is so that the eigenvectors are orthogonal, right? And if the eigenvector, so this formula, the fact that the expansion coefficients are given by these things, remember this only holds if all the vi's and wi's are orthogonal to each other and normalized. Otherwise, this formula doesn't hold. And that's why you wanted your observable to be Hermitian, so that you know that the eigenvectors have to be orthonormal to each other, so that once you like collapse, you can kind of use this formula to collapse directly on the bit that only has eigenvalue lambda. Okay, don't worry if it doesn't fully make sense. But does this make more sense than the reading, at least? Okay, good. So I've done a better job than Cohen Tanuji. That's a low bar, but okay. All right, and we'll see each other in 2 weeks or so.